In this video, we quickly review the second exam material. It focuses on LP duality and sensitivity analysis, and we started by looking at duality in linear programming, and we motivated it by considering this example where we have a small manufacturer that produces several products, and then we have a bigger manufacturer that wants to acquire this smaller manufacturer by paying a price that would be the least possible, such that this will be an offer that the smaller company cannot refuse, and the offer they can't refuse would be essentially to cover their profits while minimizing their risks because they don't have to worry about selling their product anymore. We started by saying that we have partial information about the smaller company's LP, and we are trying to see how we can utilize that information to obtain the tightest possible upper bound on the optimal objective of the smaller company, because we need to evaluate what profit they have, so that this is how much we're going to pay them for the acquisition. And then with this motivation, we considered some other example where we are essentially trying to use these multipliers for the constraints in order to obtain the tightest possible upper bound on the maximization objective. And as a result, we arrived at a dual LP. Then we called the original maximization LP Primal. We looked at the relation between the two. We saw that if we have a primal maximization LP in the canonical form where you have only less than or equal to constraints, then the dual LP is going to be a minimization problem in the canonical form, which is with greater than or equal to constraints only. And we saw that there is a correspondence between the rows of a primal and the columns of a dual and vice versa. And then we took the dual of the dual LP, and we have shown that the dual of the dual is in fact primal. Then we discussed the rules for forming the dual LP in the general case when we have all types of constraints, and we showed that if you have an equality constraint instead of the inequality, then the corresponding dual variable will be an unrestricted unsigned variable. So we saw this correspondence between equality constraints and unrestricted unsigned variables. Then if the primal LP is a maximization problem, then an inequality constraint in the less than or equal to form will correspond to a non-negative variable in the dual. Then if you have unrestricted unsigned variable, then it corresponds to the equality constraint, and then non-negative variable corresponds to greater than or equal to constraint in the dual. And we use this table to essentially formulate a dual LP for every possible case. This example demonstrates how we formulate the dual of a problem that has all types of constraints and all types of variables. And then we moved on to discussing the weak duality property, which was something that motivated duality in our discussion in the first place. Weak duality means that we are essentially obtaining an upper bound on the maximization problem by using a minimization problem. And here we went over the derivation of weak duality for the general case. It was essentially doing the same thing we did in motivating example, but doing it for a general LP. And then we said weak duality is good, but strong duality is even better. So we observed that if you have a feasible solution for the primal and a feasible solution for the dual and the corresponding objectives match, then the solutions that we found are optimal for their respective problems. And this gives us the strong duality theorem that tells you that if a primal problem is optimal, then the dual problem is also optimal and the corresponding objectives match. We discussed the idea of the proof of the duality theorem by using an example. So we essentially saw that the proof is constructive, meaning that we can construct the optimal solution for the dual based on the optimal solution of a primal. We use the correspondence between the slack variables of a primal and the dual variables in order to read the optimal solution for the dual problem from row 0 of the optimal primal dictionary. Essentially, you look at the coefficient for the ith slack variable in row 0 of a primal dictionary, and then the negative of this coefficient is going to be your optimal value for the corresponding dual variable. And this leads to one of my favorite classes of problems that I like to give for the exams, where essentially you use this correspondence between the primal and optimal dual tableaus to find the missing parameters in your LP. So for example, here we have a missing objective value, but then by knowing the fact that the optimal solution of the dual will be given by this entry right here, and then we can easily find the optimal dual value by just plugging in this optimal dual solution and the dual objective, and this will give us the optimal z value as well. Then we moved on to discussing the correspondence between the primal and dual LP types. We saw from the duality theorem that if the primal LP is optimal, then the dual LP must also be optimal, so it's impossible that it is infeasible or unbounded, and because the dual of the dual is primal, this table is going to be symmetric. So then we saw that both primal and dual can be infeasible, so this case is possible. So then if one of the problems is unbounded, then the other one must be infeasible, and both of them cannot be unbounded at the same time. So this completes this table here. Then we discussed the fundamental property of LPs called complementary slackness. So this again builds on the correspondence between the slack variables of the primal and the dual variables. And essentially we went over the derivation of the weak duality, and we saw that the only way you can have the equalities here is when you have the following holding. So you have Si, the ith slack variable, multiplied by the Yi, the ith dual variable at the optimum is equal to 0. And then the same holds when you take the dual of the dual, it's primal, right? Therefore, the jth excess variable for the dual problem multiplied by the jth primal variable must also give 0, and this is the essence of the complementary slackness theorem. You can formulate it in different forms, but the main idea to remember is this correspondence right here. Then we looked at the example where we use complementary slackness to verify that a given vector is indeed the optimal solution for the primal. The way we use the complementary slackness to show this is as follows. So whenever you have a positive value for the x variable, this means that the corresponding dual constraint is going to be binding, so you can write the equality and add it to your system of equations. And whenever you plug in the primal solution in the inequalities here and you have a strict inequality, this means that the slack variable is positive, meaning that the corresponding dual variable is equal to 0. So, and you use this fact in this system for the dual that you are writing, and you solve the system for the dual, then you verify that the solution that you obtained from this system is going to be feasible with respect to the constraints that you ignored while writing the system. So once you have primal feasibility, dual feasibility, and matching objectives, it means that the corresponding solutions for the primal and dual are optimal for their respective problems. Then we discussed the economic interpretation of the dual LP and its optimal solution. We saw that essentially the optimal solution of the dual LP gives you the marginal utility of the corresponding resource. For example, if you look at the first resource constraint in our problem here, then the corresponding value of the dual variable at the optimum will give you the maximum extra amount that you will be willing to pay for an additional unit of that resource. So therefore, we have the following interpretation of the dual optimal variable values. They are called the shadow price because this is the maximum amount you'll be willing to pay on top of the regular price of that resource, such that you will at least break even in terms of the optimal solution value. So essentially, the optimal dual value gives you the amount by which your objective will increase if you have an extra unit of the corresponding resource. Then we moved on to discussing sensitivity analysis. We started with a simple case of two variable problems that we can solve graphically, and in sensitivity analysis we are focusing on analyzing the effect of changes in the problem data, such as the objective function coefficients or technological matrix or right-hand sides, on the optimal solution, and in particular the optimal basis, because once we have the optimal basis, we can easily find the optimal solution. The first case we analyzed graphically was changing an objective function coefficient, and the key insight here is that first you identify the binding constraints at the optimum. In our case, the optimal point is this C here, and the binding constraints are given by this line and this line. And for the currently optimal solution to remain optimal, what needs to happen to the isoprofit line? The slope of this line needs to be between the slopes of two lines that define our optimal point. So essentially the isoprofit line needs to stay within this cone defined by these two lines. If it is within the cone, then the previously optimal solution remains optimal. If it leaves the cone, then the optimal basis is going to change. So then the second case we analyzed was changing the right-hand side of a constraint, and here there are a couple of different cases. The first case is when the constraint that you are changing the right-hand side of is a binding constraint at the point of the optimum. Then the way we treat this point of the optimum is not by its coordinate, but as a point of the intersection of the two binding constraints, including the one that you're changing. So let's say if you're changing this one, then you're tracking the movement of this optimal point C when you try to increase the right-hand side or decrease the right-hand side. So when you increase the right-hand side, it's going to move this way along the other binding constraint. and once you reach the last point that will be feasible when you do this movement, this defines the upper bound on your right hand side. So you just plug in this point in the left hand side of your constraint to obtain the upper limit. And then when you change the right hand side of this constraint in the opposite direction, so when you keep decreasing it, the point C is gonna move to the left, and once you hit the point B, so this will be the last point that will be feasible for the intersection of our two binding constraints, and you plug in the coordinates of this point B in the left hand side of your constraint for which you change the right hand side in order to obtain the minimum right hand side that is allowable. The second case would be when the constraint for which you change the right hand side is not binding at the optimum. Then the only way the previously optimal point is not going to be optimal is when you cut it off by your constraint as you change the right hand side. So for example, if I look at this constraint right here, you can increase it to infinity. It doesn't interfere with the optimality of point C, but if you decrease the right hand side of this constraint, then this line is going to move to the left, and eventually you're going to cut off the optimal point C. In this case, to obtain the lower limit on the right hand side of your constraint, what you do, you plug in the coordinates of the optimal point C in the left hand side of your constraint, and this will give you the lower limit. In order to be able to perform sensitivity analysis in the general case, when you have more than two variables, we had to build some background concerning the simplex method in the matrix form. So we essentially tried to look at how we can express the currently optimal tableau, or a tableau at any point, or the dictionary at any point of the execution of the simplex method through the original problem data. And then when we split the data of the problem into basic, non-basic columns, then we can see that we can express xb through xn by just multiplying both sides of this equation by b inverse and moving xb to the left. But for that, we of course need to have the B inverse. And then we have shown that we can actually get B inverse from the columns corresponding to the slack variables at any step of the simplex method. So B inverse always exists when we perform the simplex method. And we can actually read it explicitly from our simplex tableau. So since we know that B inverse always exists, now we can express xb through xn, and we obtain this expression for xb, and then by plugging in xb in the objective, we obtain the expression for z as well. So this is our revised dictionary written in the matrix form that expresses our current dictionary of the simplex method through the original problem data. And then of course we can write down the corresponding tableau as well, so we just need to modify the signs in row 0 and then the constraints for the coefficients of the non-basic variables. So we saw that we can essentially reproduce the current tableau at any step of the simplex method by using the initial problem data and the information about which variables are basic and which variables are non-basic. So to build this matrix B, what you do, you just take the basic columns from your original problem data. To build the matrix N, you take the non-basic columns, and so on. So you don't need to perform simplex method steps one by one in order to obtain the current tableau, so you can do it based on the formulas given in this tableau here. So then we further discussed the close relationship between the primal and the dual problems, and we saw that when we write down the simplex tableaus for the primal problem and the corresponding tableau for the dual problem, then there is a very, very close correspondence. So if I look at these pairs of primal and dual variables that we use in complementary slackness, and whenever one variable from the pair is basic in the primal, then the corresponding dual variable will be non-basic in the dual, and vice versa. So, and this gives you the corresponding primal and dual tableaus. And then we saw that whenever the primal tableau is infeasible but the optimality criterion in row 0 is satisfied, then the dual tableau has the opposite property. So the optimality criterion in row 0 is not satisfied, but at least you have the feasible dual tableau. So which means that whenever I have a situation like this, I cannot really work with the simplex method here because my current tableau isn't feasible, but then I can switch to the dual tableau and perform the dual iterations, and then once I solve the dual, I can read the optimal solution to the primal from row 0 of the dual tableau. So this is the idea of the dual simplex method. And then to make forming the corresponding dual tableau easier, we considered this what we call my big fat explicit simplex tableau. So here we added the rows corresponding to the non-basic variables. So let's say the non-basic variable s2 is equal to 0. So we added this row that is kind of useless, but at the same time doing this allows us to easily obtain the dual tableau by just transposing the tableau that we have here. And of course we need to remember to reverse the signs for the left hand sides of the constraints. So whenever whenever we need to switch from the primal to the dual, this is a good way to build the dual tableau quickly. So, and to reiterate the idea of the dual simplex method, if the primal simplex tableau is unfeasible but all the entries in it 0 are non-negative, meaning that 0 satisfies the optimality condition, then the corresponding dual tableau is going to be feasible but not optimal. Therefore, we can switch to the dual and perform the steps of the simplex method using the dual tableau. And this will be especially useful when we change the problem data for our primal LP in a way that the previously optimal solution is not feasible anymore. So therefore, it's easier to switch to the dual in order to obtain the new optimal solution. Okay, so now we are all set for the sensitivity analysis in the general case, and we looked at several situations. So we looked at changing the objective function coefficient, changing the column of a non-basic variable, changing the right-hand side of a constraint, introducing a new variable, and introducing a new constraint. So, and here, of course, we take a full advantage of these revised simplex formulas, which express our optimal tableau through the original problem data. And this way, we can easily track how the changes in the original problem data affect our optimal tableau and see what ranges of changes are allowable, such that the previously optimal basis still remains optimal. We use this production planning example as our workhorse for sensitivity analysis, and we try to interpret also every change that we make using this particular application. So we were given the optimal solution to this problem, and from here we can easily figure out that the basic variables were x1, x2, and x6, and x3, 4, 5 were non-basic variables. And once you have basic, non-basic variables, you can easily figure out the rest of the optimal tableau or dictionary by plugging in the original problem data into these formulas here. To determine the allowable ranges, we need to pay attention to feasibility and optimality of the previously optimal basis. So the feasibility can be checked by looking at B inverse times B, and the optimality can be checked by looking at this expression here and ensuring that all of the coefficients here still remain non-positive, whereas for optimality, of course, we need to ensure that all of these are greater than or equal to 0. With all the changes that we are considering in our analysis, only one of these two parts of the formula is going to be affected, which makes analyzing these cases relatively easy. So the cases that we considered were first changing the objective function coefficient. We split it into two subcases, the case of a basic variable and non-basic variable. So the case of a basic variable is a little more complicated one because the change occurs in the vector CB here, and the way the vector CB is included in this formula is a little more complicated than the vector Cn. So it has to be multiplied by B inverse times n. If you are given the optimal tableau, then we know exactly where to read the B inverse times n. We need to look at the columns of non-basic variables, in our case x3, x4, and x5, and the matrix corresponding to these columns will give us B inverse times n. Then we need to multiply B inverse times n by CB transposed from the left and subtract from Cn transposed in order to obtain the new non-basic variable coefficients in the objective. In our case here, the change is made to the coefficient of variable x1, and we need to find the range of delta from the inequalities expressing the fact that the resulting coefficients in row 0 must all be less than or equal to 0. And this will give us the range of delta that's allowable such that the previously optimal solution remains optimal. If we are not given the optimal tableau, then we can compute this part by first solving the linear system that will give us CB transpose times B inverse, then multiply that solution by n and subtract from Cn transpose. So this is demonstrated here. We essentially replace CB transpose B inverse with this U transposed here. Then in order to compute U, we can solve the linear system B transposed U equals to CB. We solve this linear system, we find U expressed in terms of delta as we see, and then we multiply U transposed by n and subtract from Cn transposed in order to obtain the new coefficients in row 0. We need to ensure that all of these are less than or equal to 0, and this gives us the range for delta to be greater than or equal to -1. And then if you want to get the range for C1, then we need to add this range of delta to the original coefficient C1 that we had in our problem. So the original coefficient was 4, so we need to add 4 to this range here in order to obtain the range for C1. So 4 minus 1 is going to give us 3. So C1 must be between 3 and plus infinity. And usually in the problems that I give you, you need to determine the range for the coefficient and not for delta. So keep that in mind. The second case is the case of a non-basic variable when we change the coefficient in the objective, and this case is trivial because the way Cn appears in this coefficient is straightforward. So whenever I make a change to a non-basic variable coefficient, that change directly reflects in our coefficient in row 0 in the optimal tableau. If I make this change to the variable x3, then looking at the optimal tableau, all I need is the coefficient for x3 in row 0 of that tableau, and this will give me the upper bound on increasing my coefficient value such that the previously optimal basis remains optimal. So if I look at the optimal tableau, we see that the coefficient for x3 is 4/3. This means that delta is less than or equal to 4/3, and my C3 is going to be less than or equal to 5 plus this range of delta, and is greater than or equal to -infinity. So this range of the coefficient for x3 will still ensure that the previously optimal basis and the previously optimal solution remains optimal. So this case is rather straightforward. So we have a name for this non-basic variable coefficient in row 0 of the optimal tableau, so we call it the reduced cost. So this is by how much we need to reduce the cost of production of 1 unit of our corresponding product in order for us to make sense to actually produce this product, so for it to enter the basis. Alright, so then we discussed a more general case of changing a non-basic variable column. So we saw that in the last example we only changed the non-basic variable coefficient in the objective, but if we change the whole column to that variable, the situation is not much different, and economically this case corresponds to modifying the production process for our product, perhaps reducing the amount of resources that we use and increasing the profit per unit, and we try to see what type of changes we need to make in order for us to make producing this product economically reasonable. That change in the column will correspond to essentially changing the optimal basis, right? So in our case here, the previously optimal basis will remain optimal as long as this inequality relating these deltas is satisfied, and if it's not satisfied, then the variable x3 is going to enter the basis and the optimal basis is going to change. But what's important is that the previously optimal basis still remains feasible, and with any changes in the objective function coefficient, the previously optimal basis will still remain feasible, and to find the new optimal solution in case we are outside of the range with the delta, we just need to apply a few more iterations of the simplex method. The same is the case when we introduce a new variable. This case is essentially covered by the previous situation where we were changing the non-basic variable coefficient. So when we introduce a new variable, we can treat it as an old variable, but such that it had all the coefficients equal to 0 in the original problem data before, and now we are changing it to this column right here. So then the situation pretty much reduces to what we already discussed. And things get different when we change the right hand side of a constraint. So because in this case you can actually violate the feasibility, and to verify whether it is the case, what we need to do, we need to compute B inverse times B. So now we are looking at the feasibility criterion. The optimality part is not impacted by this change, but computing the new B inverse times B, we can read B inverse again from the optimal tableau, as we know, and then we plug in new B that involves deltas. As a result, when we compute the new right hand side, this expression for the right hand side is going to involve delta, and you need to make sure that this is still greater than or equal to 0 in order for the previously optimal basis to remain feasible and hence optimal. And here I want to emphasize that as long as the previously optimal basis remains feasible, it's going to remain optimal. Now, if we don't have the optimal tableau from which we can read B inverse, then we can compute B inverse times B without actually computing B inverse, but instead solving a linear system. So we denote this by V, and then computing B inverse times B reduces to solving the linear system B times V is equal to B. And this is what is done in this example here. So we have BV is equal to B, we solve this system and we get the range of delta to be between -2 and 6. And then again, in order to determine the range for the corresponding right hand side, what we need to do is to add this range of delta to the original value of BI. So our B1 was equal to 4, so we need to add 4 to this range. So the range for B1 is going to be 4 minus 2 is 2, and 4 plus 6 is 10. So b is between 2 and 10 is the answer that we would require for our typical problem dealing with the change on the right hand side. Then, in case your change on the right hand side falls within this range, in order to find the new optimal solution, what you need to do is just plug in this delta, the change on the right hand side, into this expression here. This will give you the new optimal solution. If you are outside of the range though, then you would need to switch to the dual in order to find the optimal solution, since the primal tableau corresponding to the previously optimal one will now be infeasible. So in this example, delta falls within the range. Our range was between -2 and 6, and the delta that we are considering here is -1. So to find the new optimal solution is pretty straightforward. But if you look at the delta outside of the interval -2 to 6, like delta equal to 8, and we see that the previously optimal tableau becomes infeasible, but at the same time we see that row 0 has all entries that are non-negative, so therefore when we switch to dual we obtain a feasible dual tableau, and then we apply some iterations of the dual simplex method to obtain the new optimal solution to the dual, and then we can read the optimal solution to the primal from row 0 of optimal dual tableau. Alright, so when we introduce a new constraint, at first it seems that it affects everything because there is a change to pretty much all the parameters of our formula. But then when we look at the details, we find out that the row 0 coefficient doesn't really change. Everything remains the same as before. So, and in reality, introducing a new constraint only impacts the feasibility. So as a result, in order to find whether the previously optimal solution still remains optimal, all we need to do is to check if that solution satisfies the new constraint. If it satisfies the new constraint, then it remains optimal because effectively you just reduce the feasible region. But since the previously optimal solution is still in there because it was optimal for a larger region, obviously it's going to remain optimal for a smaller region. But then if you did cut out the previously optimal solution, then again what you need to do, you need to switch to the dual and find the new optimal solution for the dual, and then read the optimal primal solution from the optimal dual tableau. Alright, so in summary, looking at these three cases here, we saw that the corresponding changes impact only row 0 here and don't impact the feasibility. Therefore, even if we are outside of the allowable range, we can find the new optimal solution by applying the simplex iteration to the previously optimal primal tableau. And in these cases, when we change the right-hand side or introduce a new constraint, we actually impact the feasibility, but the optimality criterion still remains satisfied. Therefore, if the change is outside of the allowable range and some of the right-hand sides become negative, then what we do is switch to the dual simplex and find the optimal solution of the primal from the dual simplex tableau. And finally, the last topic is computer-based sensitivity analysis. So a typical LP solver provides the ranges for the right-hand side changes and for optimal objective coefficient changes such that the previously optimal solution remains optimal. And here if you look at the report from Lingo, for example, then we can see that there are objective coefficient ranges. So Lingo output provides the ranges. So these are the values of delta that they give, but actually you have to keep in mind that for the allowable decrease it is given in absolute terms, so meaning that if let's say the allowable decrease is 25 and the allowable increase is infinity, then our range for delta is actually between -25 and plus infinity. Then since Solver already provides all the ranges for us, then all we need to do is just to be able to interpret what exactly is happening here. And typically when we are asked a question about how a certain change reflects on the optimal solution of our previous LP, the first thing we do, we look at whether this change is within the allowable range reported here. Then if it is outside of the range, then we cannot really directly answer the question. We would need to do some extra work, such as finding the new optimal solution. But if the change falls within the range, then there are certain questions that we can answer. So for example, If we have a change in the right hand side that's within the range, then we know that the optimal value for the corresponding dual variable gives us the shadow price. So dual price is exactly the same thing as the shadow price. For example, for this constraint here, the allowable range of increase is 2, so we can increase the right hand side by up to 2 units and use this information for the dual price. If I increase the right hand side here by 1 unit, let's say, then the objective is gonna change by negative 20 times 1, so the objective is going to decrease by 20 as a result. On the other hand, if I reduce the right hand side of this constraint by 1 unit, then the objective is going to increase by 20. And you have to keep in mind that here we have the greater than or equal to constraint in the maximization problem. So you see this formulation is not in the canonical form, which means that whenever I have a greater than or equal to constraint in maximization problem, then the corresponding dual variable is actually non-positive. If I multiplied both sides of this constraint, let's say by -1 and put it in the canonical form, then the dual variable would become non-negative and this would change to 20 here. But situations of this sort are easy to sort out when you think about the physical interpretation. So for example, here we are requiring that x1 is at least 88. So if I increase the right hand side from 88 to something higher, I will reduce my feasible region, which means that my objective is going to go down, so it's going to get worse because my feasible region gets smaller, so I have less options to work with, right? And then on the other hand, if I reduce the right hand side here, then I expand my feasible region, and as a result the objective increases. So having a negative sign for the dual price makes perfect sense here. And probably the most complicated question related to computer-based sensitivity analysis is to consider whether introducing a new product makes sense. So when you introduce a new product, this is essentially the same thing as introducing a new variable in our sensitivity analysis. So a new variable comes with a column of coefficients for this variable in the objective and in the constraints, and then in order to price out that new variable, what you need to do, you essentially need to write down the coefficients for this variable next to dual prices. So for example, if the coefficient in the first constraint is A13, in the second constraint A23, and so on in the sixth constraint A63, then what you need to do, you essentially have the scalar product of these two vectors. So you multiply each dual price by the corresponding AI3 and sum up the results. So this product will give you the change in the objective due to the use of the resources by the new product. And then you need to compare that change to the coefficient in the objective. So essentially what you're computing is Cn transposed minus Cb transposed B inverse times n. And you're looking only at the column of n, both here and here, corresponding to this newly introduced variable. Then Cb transposed B inverse is given by this vector of dual prices. So you just need to multiply that vector by the newly introduced column and subtract from the profit that you get from this product. And then if this is greater than 0, then the answer is yes, produce. And if it is less than or equal to 0, then the answer is no.
Let's get this party started.
I'm just chilling with the guac from my chip hat. I know.